So, what if I told you that the answer to some of today's most frustrating software problems, the brittleness, the endless bugs, the technical debt, was actually solved 100 years ago, and not in some high-tech lab, but on the muddy, broken-down roads of Central Europe? Well, today, we're going to dig into this amazing blueprint that connects a revolutionary car from the 1920s to the future of AI-native software. It's a wild story.
Okay, let's just jump right in. Look at this old car, right? It's struggling on a really rough road. And you might think, oh, it's just a simple mechanical failure. But here's the thing. The reason it's failing is the exact same reason that your complex software applications crash and buckle and become a total nightmare to maintain. It has nothing to do with the individual parts. It's all about the philosophy that's holding them together. So, what was it? What did they miss? What was that one fundamental flaw in their thinking that somehow we are still repeating today in a totally different world? Well, that's the central mystery we're going to unravel right now.
To find the answer, we've got to look at two revolutions that are running in parallel. The first one is in automotive engineering, which kicked off way back in 1923. The second one, it's in software, and it is happening as we speak.
Now, this is where it gets really interesting, because when you look at this table, you see how perfectly history is lining up. Back in the 1920s, the status quo was basically a horse-drawn carriage with an engine bolted onto it. They called it the motorized carriage. Well, today, our status quo is what we're calling ladder frame code. It's manual, it's rigid, and it's always on the verge of breaking. The disruptor back then was this quiet genius named Hans Ledwinka. Today, it's the AI architect. And the key tech? Well, that shifted from a physical backbone chassis to an AI-driven context spine, which is all managed by something called LLM orchestration, which is just a fancy way of saying we're using a large language model to coordinate all the moving parts. Let's get a little more specific here. The motorized carriage was built by literally stacking heavy components on top of a big ladder-like frame. And on any road that wasn't perfectly smooth, it would just rattle itself to pieces. Our software today is built the exact same way. We stack libraries and frameworks together with tons of manual, boilerplate code. And yeah, it feels solid until you hit the bad roads. The edge cases, the changing requirements, and then the whole thing just becomes incredibly brittle. And that brings us to the breaking point. What happens when you take these rigid, stacked systems and put them under real-world stress? Doesn't matter if it's a rocky road or a complex cloud environment, the result is always the same: catastrophic failure. So Hans Ledwinka, he's watching these cars just shake themselves apart, and he has this massive realization. It wasn't that the engines were bad or the wheels were no good. He said it himself. The problem wasn't the parts, it was the architecture. And that is the crucial insight here. You can't fix a fundamentally flawed design just by improving the components. So back in 1923, here's what that looked like. A car hits a pothole with one wheel. Because the whole frame is one single rigid ladder, that shock twists the entire structure. And if you do that enough times, you get structural fatigue. Bolts start to snap. The chassis cracks. The car is literally tearing itself apart. Okay, now fast forward 100 years. A developer changes one single line of code in a database, and all of a sudden the user interface on the complete other side of the application breaks. Why? Because the code is a rigid, interconnected ladder. A change in one spot sends a shock wave that twists the whole system. We call this technical debt, but let's be honest, it's really just structural fatigue in digital form. So, if the ladder frame is the problem, what's the solution? This is the aha moment in both revolutions. It wasn't about building a better ladder. It was about getting rid of the ladder completely and replacing it with a spine. And this just perfectly illustrates Ledwinka's genius. He designed the backbone chassis. So instead of a wide, flat ladder, it's a single central tube that gives it immense torsional rigidity, which means it just does not want to twist. It's incredibly strong, but also super lightweight. And the best part? The drive shaft, the most critical part connecting the engine to the wheels, is protected right inside of it. Brilliant. This slide shows how all the pieces just click together into this revolutionary new thing. First, you start with that backbone tube. Then you attach independent swing axles, which means each wheel can react to the road without twisting the chassis. Next, you mount a light, air-cooled engine on the back for better balance. And now, with no engine up front and no heavy frame, you're totally free to create this beautiful, aerodynamic teardrop shape.
And just like that, you've got a car that glides over bad roads and is incredibly fast on highways. Okay, now for the mind-bending part. Let's apply that exact same logic to software. The modern equivalent is what we call the AI backbone. It's a central context spine that holds the core business logic, the intent of the application. And instead of writing manual code, the system's logic is extruded right from this central understanding. I mean, seriously, the parallel here is uncanny. First, you define the context spine. Then you add agentic swing axles. These are autonomous AI agents that handle specific jobs like security or data validation, all on their own. You connect all this to an LLM orchestration engine. And what do you get? You generate liquid software, code that can actually adapt and regenerate itself around new requirements instead of just breaking.
Of course, revolutions like this, they're not just about technology, right? They're always about people. And more often than not, they're driven by brilliant minds who push each other, challenge each other, and end up refining each other's ideas. Back in the 1920s, the key dynamic was between Hans Ledwinka, the purist, the architect, and Ferdinand Porsche, who was the great optimizer. They were friends, but they were also rivals. Porsche saw what Ledwinka was doing with the backbone and was just blown away. But he also saw how to refine it and make it work for mass production. Their validation rivalry is what took a genius idea and turned it into the VW Beetle, which, completely changed the world. And today, we need that exact same dynamic. We have the AI architect, that's our new Ledwinka, who is obsessed with the structural purity of the AI backbone. And we have the optimizer, our new Porsche, who uses AI to make the user experience absolutely perfect. One makes sure the system can handle the bad roads, and the other makes sure it just flies on the highways. So here's the crucial shift in thinking. The competition is just not about who can write the most lines of code anymore. It's about who can define a more elegant and robust intent, a better vision for what the system is supposed to be. The AI, it handles the how. The humans, we provide the what and the why. All right, so finally, let's take a look at the legacy of this whole philosophy. What actually happens when you really commit to an integrated backbone-first design? This, right here, might be the most powerful proof of all. Today, a full century later, Tatra trucks are legendary for their ability to cross the world's absolute harshest terrain. And what's at their core? The exact same backbone tube chassis that Ledwinka designed. It survives where modern ladder-frame trucks literally snap in half. Now that is the power of a superior architecture. So this table really just sums the whole thing up. The philosophy shifts from the chassis is the machine to the context is the code. The core innovation moves from a physical backbone tube to a semantic LLM spine. And the human value? Well, that evolves from imagining a new physical shape to defining a crystal clear architectural intent. In the end, it really all comes down to this one simple, powerful idea. Ledwinka's genius wasn't just in engineering. It was his ability to see a totally different pattern. While everyone else was busy trying to build a stronger, better ladder, he just stepped back, and he saw the fundamental elegance and strength of a spine. And that leaves us with one last big question. The great software architects of this new era, they're not going to be celebrated for the code they write. They're going to be celebrated for the clarity of the intent they define. So you have to ask yourself, is your team still trying to patch up the cracks in a motorized carriage, or are you ready to build the spine for the future?